Hello everyone. In today's video, we'll learn about BJT, that is Bipolar Junction Transistor. Here we'll understand what is Bipolar Junction Transistor, what is its use, how it can be used in a circuit, and the biasing configurations. So, as an introduction of BJT, what we understand, what kind of device it is. So the first point I have included, that is, it is basically an electronic device, that is a discrete electronic device that is used in most all the common circuits, all the electronic circuits where we'll be having, definitely we'll be having some of BJT device. So initially the BJT device was most probably it was used, but nowadays it has converted into the ICs, and so most of the BJTs cannot be found in practical latest circuits. Uh, so why it is called bipolar junction transistor? Definitely it is coming from the concept that is it uses both electrons and holes as a charge carriers. So in case of BJT, both electrons also will be responsible for the contribution of current as well as the holes. And it is also called as current control current device because this device uses input current to control the output current. Generally, input current will be taken as base current and the output current will be taken as emitter current in case of amplifier circuit. And according to the biasing condition, the circuit can be operated as a switch as well as in the case of amplifier. So let us see what are the different biasing concepts. So once we discuss about types of BJT, we have two different type of BJT, that is NPN and PNP transistor. In short, we say transistor. So if you see the symbol, it has three terminals, that is base, emitter and collector. And definitely all the time this base terminal will be taken at the middle, and in one end we'll be having emitter terminal and another end we'll be having collector terminal. So it is three terminal device. That means we'll be having external pins as three pins, that is base, emitter and collectors, from which we provide the biasings. So here in this symbol, what we have to observe, there is a arrow line in emitter side. So from here we cannot separate exactly. If this arrow is not there, we cannot separate which is emitter and which is collector. So this arrow justifies that the arrow side is your emitter and the another side is a collector. Now in case of NPN transistor, this arrow is moving outwards from the middle base terminal, and similarly in case of PNP transistor, if you see, only there is difference in this arrow. Here in NPN transistor, arrow is moving outwards, and in case of PNP transistor, it is moving inwards. So if we see what this arrow deals with, actually this is like we assume that this is a flow of emitter current. And how to remember this arrow, which one for NPN it is going out or for PNP it is going out. So if I just present its name as NPN, so I say this is N and this is your P region and this is your N region. So we can easily say that in the middle I am getting the P region. That means P region is something like positive charge, and we can assume that the current is moving out of positive charge from positive to negative towards. So in case of NPN transistor, this arrow will be outwards. Similarly, in case of PNP, if I say this is P positive terminal, this is, I'm just assuming this is actually a region, P type region, N type region, and again P type region. So if I assume this arrow is coming from the P region to N region. Of course, that is a direction of current. Always it will move from P positive to negative. So this is only a symbol what practically we are using for the circuits. If we see the construction of NPN transistor, so definitely there will be three regions. We call it as emitter region. This particular region is called emitter region, and in middle we have base region and the collector region. If we see the area wise how that will be divided throughout area, so the base area is the smallest area of transistor. That means base will have very small area, and as compared to collector and emitter, collector has the maximum area, and that is slightly greater than emitter region. But emitter and collector both will have huge as compared to base region. Now the density of charge carriers, density wise, the emitter region, these electrons will have higher density, and definitely this P region, that is base region, which is having very less concentration of charge carriers, and again the collector region has the higher concentration. As compared to collector and emitter will be slightly greater in concentration, and due to that concentration only we find the transistor current equation, that is total emitter current. That is total emitter current is summation of the base current and the collector current, that is I equal to IB plus IC. So generally this emitter current is measured in milliampere, and collector current also is measured in milliampere, but base current, that is very small current, so that is generally it is measured in microampere or nanoampere, picoampere, but generally practically it is kept in microamperes. Now moving to the concept of configurations. The biasing condition of transistor. So according to the biasing condition, we say that the transistor will be working in cutoff region, active region, and saturation region. These are three regions on which the transistor will work. So as we have seen in previous diagram, there is two different junctions in transistor, that is base emitter junction and collector base junction. So according to the biasing conditions, we have to check whether this base emitter junction is forward biased or base emitter junction is reverse biased. So according to its conditions, we say that when here we have four columns, region of operations, where we have written, that is cutoff region, active region, and saturation region. These are three regions on which the transistor will operate. Now the base emitter junction, the condition for base emitter junction, condition for collector base junction, and working as. So in case of cutoff region, what we see, both the junctions should be in reverse bias condition. If both the junctions are in reverse bias condition, definitely this transistor will work as an off switch. That means it will not provide any current at the output. Now in case of active region, one junction, base emitter junction, should be kept in forward bias, and collector base junction should be kept in reverse bias condition. And this is the case when the transistor is biased as an amplifier circuit. When we need to operate transistor as an amplifier circuit, this condition should satisfy. Now in case of saturation region, both the junctions should be in forward bias condition, and when this condition exists, our transistor will work as an on switch. Now moving to next slides. The biasing configurations of transistors. Generally we use three biasing configuration, that is common base configuration, common emitter configuration, and common collector configuration. In short, we say that is common base configuration as CV configuration, common emitter configuration as CE configuration, and common collector configuration as CC configurations. So one by one we just check. So in case of common base configuration, what is meaning of common base? Means here the base terminal of transistor is common. Here this is a base terminal. We have three terminals, that is base, emitter, and collector. This base terminal will be common, that is connected to the common for input and output both. And other thing, what technically we have to keep in mind, how to draw this configuration, so that the common configuration, which is with the terminal which is common, here we have base common, so that base terminal I am keeping at the bottom, and the another two terminal, that is emitter terminal and collector terminal, that remains accordingly. So I have to bias this circuit. So how to bias? So first of all, what we do, well, I'm just drawing this symbol only. We have to concentrate only on this symbol. So this is NPN transistor, right? This is NPN transistor. So as we see, if we consider this as a direction of emitter current, so first of all we have to mark the direction of emitter current. So this, if I assume this is a emitter current direction, so the same direction I have marked this emitter current, the direction of emitter current. So according to current Kirchhoff's current law, if we know that this is a current equation of transistor, that is IE equal to IB plus IC, and if I say this IE is outwards, emitter current is outwards, this IB and IC should be inwards. So according to this direction, inside this circle we have to check this direction of emitter current. So this is outwards, so same direction what I done, I have just marked it the emitter current, that is outwards. Now according to this, the another two directions should be decided. Now though this is outwards, IB and IC should be inwards. So accordingly I have marked this, IC is inwards and IB is inwards. Now according to this direction, I have to bias. That is a technique, that is only a technique. So according to this direction, if this current is coming inwards, then what should be the direction of battery? The battery direction should be negative. This polarity should be negative. Then only the current has to come. So according to this direction, I have decided the polarity of this battery, that is negative and another is positive. Similarly, now this is a direction of collector current. So when I want to bias, I have to connect the external battery. So definitely this terminal should be positive because the current is coming out of this positive, and then another is negative terminal. So accordingly we can just connect these two batteries. So at the collector terminal, once we connect a battery, it is called VCC, and for the this is not a VVB, this will be VEE. Here it is VEE, that is emitter biased voltage. Now what is this? This is actually a battery. This is external voltage what we have connected to the device. Now if we see the voltage across base and emitter, here we have a emitter terminal, here we have a base terminal, the voltage drop between base and emitter terminal is taken as VBE. Similarly, the voltage drop across collector and base terminal will be taken as VBC. Practically there will be additional resistance will be connected here, which will maintain this emitter current, and here also we have practically collector resistance which will manage this flow of collector current. So let us discuss about the current gain concept of this particular configuration circuit. The current gain of common base is represented as alpha. So current gain, I can write it as output current by input current, because this is a common, so we will not be taking this current. So the output will be taking, in case of common base configuration, output will be taking as collector current and input as emitter current. So the ratio of output current by input current, of course, as we can see from this equation, that is IE, the total emitter current is summation of base current and collector current. So obviously this collector current is less than emitter current, so this value will be less than 1. So that means this particular configuration will not provide a current gain. Now in case of voltage gain, what we see, the output voltage is taken as VBC and the input voltage is taken as VBE. So in case of amplifier circuit, this VBC will be taken as reverse bias voltage. So this is approximately 0 to 10 to 15 volt higher voltage will be applied at reverse bias region, and very less forward bias voltage is taken in case of forward junction. So if we take a ratio of these two, that will be always greater than 1. So this particular circuit is suitable only for voltage gain amplification. Now moving to next configuration, that is common emitter configuration circuit. So the common emitter configuration is, in short, we say as CE configuration circuit. In case of CE configuration circuit, again we will just approach to the technique. So as I said that which is the terminal which is common, that terminal I am just taking at the bottom. So emitter is common, so emitter terminal I have taken is at the bottom. So obviously I am just rotating the symbol. I'm not doing anything, I'm just rotating the symbol. So once emitter terminal comes down, the collector will be in opposite, and obviously every time the base terminal will be at the middle. So again I have to mark, first I have to mark the direction of current. Then according to the direction of current, we will be providing the biasings. So here we see emitter current is outwards. This is, we will just assume this is the direction of emitter current. So emitter current is outwards. When emitter current is outwards, definitely this other two currents, that is IB and IC, should be inwards according to again the Kirchhoff's current law. And already we have discussed about IE equal to IB plus IC. So when IE is outwards, this IB and IC should be inwards. Now according to this direction of current, when this current is outwards, obviously this battery polarity should be positive. And here also the direction of, according to the direction of base current, this battery also should be positive. So we have to just remember, in case of common emitter configuration, this both the biasings is kept in positive directions. So here we have we are just representing this biasing voltage as VBB and VCC. Again if we see the voltage drop across collector and emitter junction, that is VCE, and the voltage drop across base and emitter junction, that is VBE. And again I can say that this IE and IC, these are two majority carrier currents. So this is measured in milliamperes generally, and IB it is in microampere. So let us talk about current gain of common emitter configuration. So the current gain is represented as beta, and this beta can be written as output current by input current. So the output current is here IC and input current is IB. So this current is measured in microampere and this current is measured in milliampere. So obviously IC by IB will be much greater than 1. So definitely we can say this type of configuration will provide current gain. Similarly, if we can, in case of voltage gain, what we can see, the output voltage is VCE, that is reverse bias voltage. This voltage will be very much higher as compared to forward bias voltage. So if we take the ratio, this ratio will be higher than 1. So we can say that this type of configuration is provided both voltage and current gain. So overall power of the signal can be amplified by this configuration circuit, that is common emitter configuration circuit. So practically most of the times common emitter configuration circuits are used for amplifier circuits. The next configuration is common collector configuration, which is in short it is written as CC configuration. Here in CC configuration, what I have taken, collector terminal I have taken at the bottom, and if I take this as a collector terminal, the opposite terminal is the emitter and the middle is the base. So the next step is I have to mark the direction of emitter current first. Keep in mind, first we have to mark the direction of emitter current. We have to focus on emitter current. So this emitter current is outwards, this direction is outwards. So accordingly I am just marking as the same arrow it is showing here, the same direction I am marking the emitter current. The emitter current is outwards, so this IB and IC should be inwards. This both should be inwards. So according to this direction, according to the direction of emitter current, I have biased this emitter and collector. So the biasing here it is taken as negative and this is positive, that is the biasing voltage is VEE. And similarly in case of base, according to this direction, according to the direction of base current, this terminal should be taken as positive. And if we see the current gain of common collector is represented as gamma, and that is ratio of output current by input current. So that is IE by IB, which is much greater in as compared with common base and common emitter. This circuit will provide much higher current gain as compared to both. So this type of circuit is especially used for current amplifier circuits like motor driver modules, which is generally used in robots where Darlington pair concepts are used. Thank you.